Hello, in this video I'm going to talk about resistors, so another one of the fundamental components in our electrical circuits. And we tend to solve a whole load of problems and circuit analysis and all that. It's got resistors all over the place, but we don't talk about them all that much in our pre-university physics. So I'm just going to run through what they are, what they're made of, and a couple of things that they can be used for, as well as a few pointers of more complicated stuff that I won't go into in detail, but at least it points you in where you might go next when it comes to resistors. Right, so what are they made of? The really old resistors, if you go back, middle of the last century, sort of, 1950s or earlier or thereabouts, they were quite big things. You'd open up something like a TV or some other bit of equipment, you'd have these massive, great big resistors sitting around. You could see what they were quite happily because you'd have this, they would look like the things the symbols on the circuit diagrams. You'd have this great big cylindrical thing with a wire going in each end. If you cut one of them open and have a look, you'd quite often they'd be made of ceramic and powdered carbon and things like that. They could end up being a bit of a mess. This was a bit of a problem with the early resistors, that they weren't as stable with age and temperature as the modern resistors are now. They could react in certain ways, so their composition would be changing, their decay, their all manner of horrible things. They weren't that great, but that's what they were using back then. So this was all this powdered carbon and ceramic stuff. Nowadays, they got a range of things that they use, but it's mainly sort of various metal alloys, and these are more stable both with age and with temperature. They're easier to get into a range of sizes, and yeah, they just work better in your circuits. So like with all the components, they're always getting better. Sometimes they can be directional as well, depending on what it is you're making them out of. We do all these resistance calculations from the resistivity, don't we, of various materials, but sometimes that can be directional as well. So if you're trying to push current through a material that might be going through or against some kind of lattice structure, when you start looking at the chemistry of the actual material, so you've got that sort of thing you can take into account as well. So that's the makeup of them. In terms of what they're used for, there's two things when we're starting out that we're going to look at mostly, and that's changing current. Quite often we want to limit the amount of current going into a component, and if you put more resistance into a circuit, you're going to bring the current down. So that's one thing, which I'll go through in more detail in a second. And then the other one is dividing potential. We talk a lot about potential dividers and such like, and that is another thing that resistors are good at least in maybe in low power circuits, and again I'll get onto that in a moment. So let's start with changing current then. So you'll have a lot of components. LEDs are a good example, where you don't want to put too much current through them. If you've got too much current, you'll end up with too much power. You can start frying things. And LEDs, you can destroy an LED by passing too much current through it, as with many other components. So, and they quite often tell you, if you've played around in the lab at school or college, you might have already noticed this, that you might pick up, say, a red LED. You're just doing one small little circuit powered by a battery. We're not doing anything off of mains yet. So a red LED, and it might say, oh yeah, you want to have, say, 1.8 volts across it with a maximum current of 20 milliamps, something like that. That is typical. It'll vary from LED to LED, but that's a typical set of numbers. And then you say, okay, well, let's plug one of these into, say, a 3-volt battery. That's our EMF. Well, we now need to bring our voltage down, and we need to limit our current. So how are we going to go about getting this 20 milliamp current? Well, first of all, we need to get 1.2 volts over a resistor that we're going to stick in series. So we're going to have our cell. We're then going to have our resistor, which we're going to stick in series with our LED. Let's draw that in. So we've got this set up in our circuit. We want to have 1.2 volts going across here. And we know, because it's all in series, of course, that's going to be 20 milliamps as well. So this resistor is going to have a resistance of 1.2 divided by our 20 milliamps. So what's that? 600 ohms. So we want a 600 ohm resistor that we can stick in series with the LED. That means we're going to have the right current. We're going to have our 20 milliamps going through the LED. We're going to have our 1.8 volts. Everything's going to be fine. Just a quick word on that, actually, in case you were, okay, what does this mean for the resistance of the LED? Because don't they have really low resistance? Think of our IV characteristics of our diodes. You get some kind of, we've got our threshold voltage here that you need in order to get the thing to light up, and then it goes just through the roof, doesn't it? This is the diode behavior, where our resistance is dropping like crazy. Okay, you're still going to have some resistance, but it's going to be very low. So if the resistance is so low, then why are we still getting only 1.2 volts across the resistor out of our EMF of 3 volts? Well, it's because you have to take into account of this voltage drop. So when we're talking about this 1.8 volts, give or take, this is going to be saying something to do with the threshold voltage. It might not exactly be the threshold of, well, where do we kick in with just our first little bit of current? It's going to be more, well, where is this getting up to our, full brightness? This is what we're going to want. It might be that bit higher, but this is going to be the voltage that we've then got across the LED in order to create the full brightness to have the LED actually on. So it's a not the usual resistance calculation that we would make. You can't just say, oh yeah, we've got 600 ohms for this resistance, so this is going to be 900 ohms because it's split in proportion to the potential differences, because you've got a slightly different setup in what's actually happening in these diodes. But anyway, the long and the short of it is this resistor has been great in the fact that it's limited our current. If we didn't have that there, we would have had too much voltage across the LED. We wouldn't be at this 1.8 volts. We'd have, more to the point, we'd have too much current going through it. The current, you can see the current just goes nuts. You move up a little bit too much, the current is going to be really, really high. It's then going to fry the LED and we won't get any light out of it at all. And that is the key benefit with it, because you might do a power calculation and say, okay, well, let's look at then the power of the LED and the power that we're losing in the resistor. And you say, okay, well, the power in the LED, we've got our voltage, our 1.8 volts, we've got our 20 milliamps. So if we're multiplying those together, then what we get, we're getting 36 milliwatts out of this. For the resistor, we've got 24. So we are still losing, 40% of our power is just being burnt up in heat in the resistor. So it's not massively efficient. But then what do you consider massively efficient to be? Burning out the LED isn't particularly efficient. So in terms of coming up with a quick circuit that's going to fix the current, which means it's going to light up, and this isn't exactly a huge power outlay. So if you just got a low power circuit, this isn't that bad. This having that amount of power coming out of this 600 ohm resistor is not going to get that hot. It's going to be fine. Okay, you're losing a bit of power, but the whole thing works. And re-engineering it to try and come up with something better is just going to be a waste of time. So that's one thing that we've got. I mean, another thing for limiting current and such like is, okay, what if we wanted to hook this all up to the mains? So say we were talking about an actual LED light bulb that you're going to put into your light bulb fitting. So you're sitting there now at 230 volts. Now, I don't know if you've ever opened up an LED light bulb, but compared to the old filament, the incandescent ones, of course, you have to have some circuitry in the LED bulbs. It's not just the case of you've got a filament like the old days, which just acts, that is the resistor, that is the thing that's releasing the light. You don't really need anything else. You've just got a hot bit of wire stuck inside a glass protector. Now, if we got LEDs, we need some circuitry. So we've got our 230 volts. We're going to, first of all, we're going to want to get this, we're going to have a diode there. So we're just moving everything in one direction. And I'll come back to, this is where in a moment we can talk about rectifier circuits, which is quite nice. But on the cheap bulbs, you'll notice sometimes you have a bit of flicker, but we'll get back to that later on, because you can have flicker if you're just sticking the diode in and you're changing your AC to just, on off. Essentially, we're just taking the positive on the direction of the current flow. So you're more or less getting on, off, and this might be going at something like 120 hertz or something. So you're going to get this flickering of the bulb if you've got a really cheap bulb. Now I'm just going to draw in one LED on the circuit, but of course you might have more than one, and I mean you will do in a bulb that you're actually going to plug into the mains. So if you're going to compare, say we wanted to get a 60 watt, we wanted to replace our old 60 watt incandescent filament light bulb, then the efficiency of the LED, you're looking about 7 watts for an LED bulb in comparison, because we're only getting maybe 5 to 10%, and 10% is probably quite optimistic, actually released as light, visible light in these incandescent bulbs. So the LEDs are far more efficient. Now we're then thinking, okay, well, say these are slightly got a bit more oomph than the LEDs we were looking at there. Say we want to have 3 volts and 50 milliamps for each LED, and we want to now get up to, so what's our wattage going to be on that? That's going to be 0.15 watts per LED. So if we've got, say, 50 LEDs, then that's going to be 7.5 watts. So that seems reasonable, doesn't it? So we now want 50 LEDs inside the bulb, which is why I'm not drawing out 50 of these symbols in the circuit diagram, which means we need 150 watts, 150 volts across all of our LEDs, and then we need the other 80 volts across the resistor. Or it may even be 2 resistors. You could split this up. You could have, quite often you'll see 2, 3 resistors inside, but I've just drawn it as 1 resistor in the diagram, in the same way as I've drawn 1 LED in the diagram. So what are we going to need then if we've got 80 volts and we've got 50 milliamps? So what's that going to be? 1600 ohms is what we're going to need as our resistor. You can then say, okay, we're still losing energy there in the resistor, because we're going to have our I squared R on this, aren't we? We're going to have our 50 milliamps, so our 0.005 squared multiplied by 1600, whatever that's going to come out as. So we're still losing a reasonable amount of power here. Let's actually make these changes, and so let's do that calculation. So 0.05 times 0.05 times 1600, so we can get rid of 1212. So that's going to be 1/4 of 16. So we're losing 4 watts going through the resistor. But so what? Even then, the combination of having 7.5 watts for our LEDs and 4 watts for heat from the resistor, that's still only 11.5 watts compared to 60 watts if we had the incandescent bulb. So, it depends what you consider to be inefficient. We're still losing this out of our actual supply. We're wasting a bit of energy there, but so what? It's still a massive improvement on what we would have had before. And if we don't have it there, again, we're going to end up blowing the LEDs. So it's horses for courses on these things, and this is a much better outcome than what we had previously. So there you go. So that's what we've got there on changing current. So now let's think about dividing potential. That's the other thing. And we're always drawing out these circuit potential divider things in our circuit diagrams. A typical sort of thing that we see is something like this. You'll have these two resistors which are connected in series. We'll say this is our input voltage, and then we'll connect something over one of the resistors, and this will be our output voltage. Now this can get drawn in lots of different ways. Is one of the things that can throw people when they start looking at circuit diagrams drawn elsewhere. You know, one thing that can change is that you'll get some people will draw the resistors looking like this rather than the little rectangles that we draw, and then you get others where they put in as well, say an earth point. So say you've got you might get a diagram. Actually, let's go completely different and draw in the wiggly lines as well. So you could have resistor there, and then you might go on a bit, come down. Let's have another resistor here, and then let's have an earth down there, and then another connector over there. So this is actually the same circuit. It just looks very different. So that'll be our V in, that'll be our V out, and then this is earth down here. So the reason this is the same is, remember, we're just thinking in terms of potential differences. So you've got various potential points. You know, on this top diagram here, you could say, well, that is our in and this is our zero. So you could have V in and 0 volts. So everything down the bottom here is 0 volts, which is what we're saying this earth is down there. That's our 0 volts. So this bottom diagram is more talking about potentials rather than potential differences. So it's the same thing. You know, when we draw this top picture, we're quite often saying, well, V in is the difference between this top potential and 0 at the bottom. So whether you think of V in as being just the potential at the top or the difference between that and the bottom, it's all the same, really. So that's why these two diagrams end up being the same thing. And if you then plug in something on this part of the circuit, so continuing on this bottom one, you plug in something here with some, whatever this would be, some thing going on here, some bit of circuitry, which then goes off to another earth. Well, you can now see we got the same. This is V out again, and the potential difference is V out minus 0. So you can see how these circuit diagrams can get drawn in different ways. But yeah, these potential dividers then, so it is a way of, if we want to like do sensing, you get a lot of sensing circuits where you're looking at how potential might be changing. So we've seen these things before. You know, you might change that to an LDR. So if you've got a light dependent resistor in there, that's then going to change the output potential there. So you can sense that and determine if the light intensity has changed. You can have it on a slider, like you might actually have a variable resistor, a volume control or a light dimmer switch, that sort of thing, where this connector is actually going to be on that resistor, moving up and down, changing how the potential is split. You know, if you've got the arrow all the way down the bottom here, then you're going to have a lower V out because you've pushed more of the resistance into the other part of the circuit. If you put the arrow at the top, you're going to have a higher V out. So you're moving your output potential up and down depending on how you're rotating the dial. Now these are fine up to a point, but of course whatever you plug in across here, going on this first picture, whatever you're plugging there, if you've got something which has got high power in the output, then this ain't going to be a great idea for plugging it across this. If you've got a high power output there and you plug it in here, you're going to be drawing a lot of current, and all of that current has to go through that first resistor. Now that means you're going to get a lot of energy loss in there. You're going to get a lot of heat in that first resistor because you've got the I squared R. And if you've got that resistor sitting there, it's going to have a fairly significant R. You start drawing significant current, you're going to have problems. So this setup is fine if you've got a low power output on whatever it is you're connecting to the circuit. So if you're doing some kind of sensing thing, or you're just dealing with you know, a volume control that can then feed in to an amplifier, and the amplifier can handle then dealing with the power going off to the speakers and such like. You don't want to run it all through this directly. You'd want to connect it off to something else. So say these are like linear regulators, which they're not that efficient, and that's why they're good at low power. They're simple and they're fine at low power. If you want to go to high power, then of course you've got other options. If you want to change your voltage, you want to drop down your voltage, which is what this is doing, then you've got the option of using a transformer that can take your mains voltage and dropping it down to something lower. So that would be a better alternative. You can have these things called buck converters, which are more efficient and effective circuits designed for reducing voltage and increasing current. So you've got that instead of using these linear regulators. So you've got those options. Another thing that you can use in circuits in order to reduce the waste in these resistors is to have relay circuits. So you'll see this on maybe the old style street lamps. So if you've got your street lamps when they were still using the actual the bulbs, you'd have a switch, you'd have your bulb. This would be connected to your mains supply, so you'd have your 230 volts. Now you don't want to be sticking in your light dependent resistor into this in order to determine whether it's going to come on or off or not. You don't want to be sticking just an LDR and a resistor in here, because you're just going to be burning up wattage all the time when the light comes on. So it's nice to have this simple circuit, but you want to connect this switch then to a relay, which is like this sort of magnetic thing, which is going to, when the current's flowing through the coil, is going to flick the switch closed and then turn the light on. And then you can connect that up to say a 9-volt DC circuit or something like that, with all manner of circuitry going on, which is going to have various transistors and other such things kicking around in all of this. So you'll have your LDR will be sitting in this, determining what's going on. That's going to be turning on the 9-volt circuit. So you'll have all manner of other resistors. You'll probably have another transistor kicking around as well. But however you want to decide setting this up, we don't really care about this at the moment. That circuit with the LDR will then turn on the main circuit for the bulb. And that means when it's sitting there not doing anything, you're not going to be losing much power, because everything's just sitting there on low voltage on this alternative circuit, and then you have the relay switch in between. So there's lots of other alternatives if you're wanting to work with different voltage sources, and you're wanting to go high low or low high, and you want to reduce your power losses and all of that. So transformers, buck converters, relays and such like are good ways to go on that. But really for this, we're just trying to get this idea, why are we putting all these resistors in? We saw in the previous examples that if you don't have them there, you're going to burn through all those LEDs, and LEDs are giving you a much greater efficiency anyway, so that energy loss doesn't matter too much. And then we've got these potential dividers in these low power systems for sensing and volume control and light control and things like that. So yeah, hopefully that just gives you a better idea of why we're putting these resistors in. They're not just sitting there getting hot for no reason. They're not just sitting there burning up our power and giving us exam questions to answer. Yeah, they do have fundamental uses when we're building our circuits.